Imagine waking up one morning and everything looks normal. The sky is blue, the birds are singing, your coffee is hot. The news is playing in the background. Nothing seems wrong. Nothing feels different. But something has changed overnight. Something invisible. Something that most people never think about, never see, never feel. And yet something that has been protecting every single living creature on this planet for 4.5 billion years. Earth's magnetic field is gone. Not weakened, not shifting, gone. And you have no idea. Neither does your neighbor, neither does your government. Not yet. Because in the first hours after the magnetic field collapses, the world still looks exactly the same. The catastrophe is invisible, silent, moving at the speed of light, literally, as the sun sends its first unfiltered wave of charged particles racing toward a planet that no longer has its armor. This is not science fiction. This is not a fringe theory buried in some obscure corner of the internet. The scenario of a geomagnetic field collapse has been studied by NASA, the European Space Agency, and leading geophysicists at institutions including the University of Leeds, Columbia University, and the GFZ German Research Center for Geosciences in Potsdam. Scientists have modeled it. They have run the simulations. They have looked at the geological record, the actual rock record, of moments in Earth's past when the magnetic field dropped to near zero. And what they found is deeply unsettling, because it has happened before, multiple times. The last full geomagnetic reversal, known as the Brunhes-Matuyama reversal, occurred approximately 780,000 years ago. During that process, the field did not simply flip like a switch. It weakened. It fragmented. It left parts of the planet temporarily exposed to the full force of the solar wind. Today, we know the field is weakening again. The South Atlantic Anomaly, a vast region stretching from South America across to Southern Africa, already shows magnetic field strength dramatically lower than the global average. Satellites passing through this zone experience increased radiation exposure. Some electronic systems malfunction. The European Space Agency's Swarm satellite constellation has been tracking the field's behavior since 2013, and the data shows the field has weakened by approximately 9% over the last 2 centuries. 9% in 200 years. That is not a slow drift. That is a trend. But for this investigation, we are not going to model a gradual weakening. We are going to ask the harder question, the darker question. What if it happened suddenly? What if you woke up one morning, poured your coffee, and the field was simply gone? What would the first 72 hours look like? Hour by hour, layer by layer. From the invisible devastation in the upper atmosphere, all the way down to the streets where you live, the food in your refrigerator, the phone in your hand, and the cells inside your own body? That is what we are going to find out. And I warn you, some of what science tells us about those first 3 days is far more terrifying than anything Hollywood has ever imagined. Let's begin. To understand what happens when the magnetic field disappears, you first need to understand what it actually does, because most people have a vague sense that it involves compasses and the North Pole, and that is about as far as the mental model goes. The reality is far more extraordinary. Earth's magnetic field, technically called the magnetosphere, is generated deep inside the planet. At the center of the Earth sits a solid inner core of iron and nickel, roughly the size of the Moon, at temperatures exceeding 5,000 degrees Celsius. Surrounding it is the outer core, a churning, convecting ocean of liquid iron approximately 2,200 kilometers thick. As this liquid metal flows, driven by heat from the inner core and influenced by Earth's rotation, it generates electrical currents. Those electrical currents generate a magnetic field. The whole system is called the geodynamo. The field extends far out into space, not in a perfect sphere, but in a teardrop shape, compressed on the side facing the sun and stretched into a long tail on the night side, sometimes extending hundreds of thousands of kilometers behind the planet. This structure is what scientists call the magnetosphere, and it acts as an invisible force field, deflecting the constant stream of charged particles that flows outward from the sun in all directions, known as the solar wind. Without this deflection, the solar wind would strip away the upper atmosphere over geological timescales. We know this is not just a theory. We have a nearby example: Mars. Mars lost its global magnetic field approximately 4 billion years ago, and over the following billions of years, the solar wind gradually eroded its thick, warm, wet atmosphere. Today, the Martian atmosphere is less than 1% the density of Earth's. Its surface is a frozen, irradiated desert. That is the long-term consequence. But what happens in the short term? What happens in the first 3 days? This is where the science gets very specific and very dark. The magnetosphere does several things simultaneously. It deflects the solar wind. It traps high-energy particles in radiation belts, the Van Allen belts, discovered in 1958 by instruments on America's first successful satellite, Explorer 1. It channels incoming charged particles toward the polar regions, where they interact with the upper atmosphere to produce the auroras. And critically, it blocks a significant portion of the cosmic radiation that constantly bombards Earth from all directions, not just from our sun, but from distant supernovae and other high-energy events across the galaxy. Remove the field, and all of those functions stop. Simultaneously. Instantly. The solar wind hits at full force. The Van Allen belts, without the field to maintain them, begin to collapse and dump their stored radiation. Cosmic rays pour in at elevated levels. The upper atmosphere, suddenly exposed, begins to interact with charged particles in ways that have profound consequences for the chemistry of the ozone layer. And all of this begins in the first minutes. Not the first days, the first minutes. The speed of light from the sun to Earth is approximately 8 minutes, meaning that whatever the sun is doing right now, we will feel it 8 minutes later. The moment the field collapses, the solar wind, traveling at speeds between 300 and 800 kilometers per second, begins hitting the upper atmosphere without any magnetic braking. The leading edge of consequences arrives almost immediately. What does that look like? What does the world experience in those first critical hours? That is what we are going to explore, chapter by chapter, hour by hour. Because the story of Earth without its magnetic field is not a story about a distant future catastrophe. It is a story about physics, about biology, about infrastructure, about everything our civilization has quietly assumed will always be there. The shield has fallen. The clock is running, and we have 72 hours. The field is gone. You do not feel it. You cannot see it. There is no sound, no shock wave, no visible sign that anything has changed. The morning light looks exactly the same. The temperature outside is normal. Birds are still moving through the sky. Children are walking to school. But 8 minutes ago, the sun sent its first unobstructed volley of charged particles toward a planet that no longer has its deflector shield. And those particles are already here. They arrived quietly. At the speed of the solar wind, somewhere between 400 and 800 kilometers per second, the first wave of protons and electrons slammed into the upper atmosphere without any magnetic field to curve them away, slow them down, or redirect them toward the poles. For the first time in hundreds of thousands of years, the full force of the solar wind is hitting Earth's atmosphere head-on, across the entire surface of the planet facing the sun. And the atmosphere is fighting back. For now. This is the first critical thing to understand about the scenario. Earth's atmosphere itself provides a layer of protection, particularly the stratosphere and the dense lower atmosphere. The initial wave of solar wind particles does not instantly reach the ground. The atmosphere absorbs and scatters a significant portion of the incoming radiation, but it is doing so at enormous cost. Chemical reactions that would normally never occur, or occur only at the poles during intense auroral events, are now happening globally in the upper stratosphere, at altitudes between 15 and 50 kilometers above the surface. The target is ozone. The ozone layer. That invisible chemical shield, just a thin band of triatomic oxygen molecules sitting in the stratosphere, blocks approximately 97 to 99% of the sun's ultraviolet B and ultraviolet C radiation. Without it, the surface of the Earth is exposed to wavelengths of light that destroy DNA, that cause mutations, that kill microorganisms, damage plant cells, cause cataracts, suppress immune systems, and dramatically elevate rates of skin cancer. Scientists at the University of Southampton and at NASA's Goddard Space Flight Center have modeled what happens to the ozone layer during intense solar proton events. Moments when the sun fires massive bursts of high-energy protons toward Earth. Even with the magnetic field in place, a sufficiently powerful solar proton event can destroy measurable percentages of polar ozone within hours. The event of October and November 2003, known as the Halloween storms, produced solar proton fluxes intense enough to cause significant ozone depletion over the Antarctic, detectable by satellites for weeks afterward. Now imagine that process happening globally, continuously, without the magnetic field filtering and redirecting the incoming particles, without the protection of the Van Allen belts. The ozone destruction begins in the first hour, silently, invisibly, kilometers above anyone's head. It will not reach critical levels immediately. The ozone layer does not vanish in 60 minutes, but the chemistry has begun. Nitrogen oxides, produced when high-energy particles collide with nitrogen molecules in the stratosphere, are the primary agents of ozone destruction in this scenario. They are catalytic destroyers, meaning a single nitrogen oxide molecule can destroy thousands of ozone molecules in a chain reaction before being neutralized. With particle bombardment now occurring globally and continuously, these catalytic chains are running simultaneously across the entire upper atmosphere. By hour 3, satellite instruments, if they are still functioning, would detect measurable ozone column reductions across equatorial and mid-latitude regions. Areas that had previously been protected from polar ozone dynamics are now showing the same signatures. Scientists monitoring atmospheric data would be watching numbers they have never seen outside of extreme polar events, now appearing at latitudes over North America, Europe, but we are getting ahead of ourselves. Because in hour 0 and hour 1, the crisis that is most immediately visible to the handful of people paying attention is not happening in the atmosphere. It is happening in orbit. There are currently more than 8,000 active and inactive satellites in Earth orbit. They form the invisible backbone of modern civilization. GPS navigation, weather forecasting, financial transaction routing, military communications, broadband internet, television broadcasting, scientific observation, emergency response coordination. The entire architecture of the connected world depends on hardware sitting in space, above the atmosphere, directly exposed to the space environment. Those satellites are now in serious trouble. Even with the magnetic field intact, satellites in low Earth orbit routinely experience radiation exposure. The Van Allen belts are well-mapped hazards that spacecraft engineers design around. Solar energetic particle events require satellite operators to put instruments in safe mode. These are known, manageable risks within the context of a functioning magnetosphere. Without the magnetosphere, the radiation environment in Earth orbit becomes something entirely different. The Van Allen belts themselves, the inner belt sitting roughly between 1,000 and 6,000 kilometers altitude, the outer belt between 13,000 and 60,000 kilometers, are not immediately gone. They are structures of trapped particles held in place by the magnetic field. Without the field, they begin to destabilize. The particles that were trapped begin to migrate. Some are dumped into the upper atmosphere. Others escape into space. The process is not instantaneous. It unfolds over hours and days. But during that process, the belts go from being relatively well-understood hazard zones to unpredictable, dynamic storms of radiation moving through orbital. Satellites designed with radiation shielding, calculated for normal Van Allen belt exposure, are now facing flux levels their engineers never planned for. The first satellites to experience catastrophic failure are likely those in medium Earth orbit, the region where GPS satellites operate, at roughly 20,000 kilometers altitude, sitting directly within the outer Van Allen belt's destabilization zone. GPS satellites from the American Navstar constellation, Russia's GLONASS, Europe's Galileo system, and China's Beidou are all vulnerable. Their electronics, even with radiation hardening, face exposure levels that can cause single-event upsets, latch-up conditions, and permanent damage to solar panels and sensor arrays. Within the first 2 hours, ground control stations around the world begin receiving anomalous telemetry from their satellite assets. Some satellites begin returning corrupted data. Others go into automatic safe mode, shutting down non-essential systems to protect core electronics. A small number, older satellites with less radiation hardening, or those caught at particularly bad orbital positions, experience complete electronic failure and go permanently silent. The GPS signal begins to degrade. Not uniformly, not all at once, but enough that timing errors start appearing in systems that depend on GPS not just for navigation, but for precision timekeeping. Financial markets use GPS timing to synchronize transactions across global networks. Cellular tower networks use GPS timing to coordinate frequency allocation. Power grid systems use GPS timing for phase synchronization across vast transmission networks. Small timing errors, accumulating silently in background systems, begin to create subtle problems that no single operator can yet identify as part of a global event. Meanwhile, in the ionosphere, the electrically charged upper layer of the atmosphere between about 60 and 1,000 kilometers altitude, something dramatic is happening. The ionosphere is normally a relatively stable reflector of radio waves, enabling long-distance HF radio communication. The influx of solar particles is ionizing additional atmospheric layers, creating what radio engineers call ionospheric storms, massive disruptions to the electron density that make radio wave propagation unpredictable and unreliable. Long-distance HF radio communication begins to fail. Blackouts appear across entire frequency bands. Aviation, maritime, and military systems that rely on HF as a backup communication method start reporting problems. Pilots over oceanic routes, where satellite communication supplements but does not completely replace HF radio, begin experiencing communication difficulties. Air traffic controllers notice, but at this point, they do not know why. Here is something that most discussions of this scenario completely overlook. The magnetic field is not just an external shield. It is a navigational reference that biological systems have been using for hundreds of millions of years. Long before humans built compasses, long before we understood magnetism as a scientific concept, long before we had any conscious awareness of the planet's magnetic field at all, animals were using it, precisely, reliably, across generations. The evidence for animal magnetoreception, the biological ability to sense magnetic fields, is now extensive and scientifically well established. Research published in the Journal of Experimental Biology, in Nature, and in the Proceedings of the National Academy of Sciences has documented magnetic field sensing in species including homing pigeons, European robins, sea turtles, sharks, salmon, honeybees, migratory whales, and even cattle. The mechanisms vary. Some species appear to use cryptochrome proteins in their eyes, which are sensitive to magnetic field direction through quantum mechanical processes, a discovery that earned the nickname quantum compass. Others appear to have magnetite crystals, the same mineral as compass needles, embedded in tissues near the head or the lateral line system. In 2019, researchers at Caltech, led by Joseph Kirschvink, published evidence suggesting that human brains also respond to magnetic field changes at the neural level, though whether humans consciously perceive this or use it for navigation remains debated. For migratory animals, the magnetic field is not a convenience. It is the map. Sea turtles navigate thousands of kilometers of open ocean using the magnetic field as a coordinate system, distinguishing both the intensity and inclination angle of the field to determine their position with remarkable precision. Research by Kenneth Lohman at the University of North Carolina has demonstrated that loggerhead sea turtles can detect regional magnetic signatures and use them as navigational waypoints during their transoceanic migrations. Salmon use the field to return from the open Pacific to the precise river systems where they were born, sometimes to the exact tributary. Homing pigeons use it as one component of a multi-layered navigational system that also includes sun position and olfactory cues. The moment the field collapses, every animal using it for navigation loses its primary positional reference. Simultaneously, globally. Migratory bird flocks in mid-journey, crossing continents and oceans, lose their magnetic compass. Salmon in the open Pacific lose their homing signal. Sea turtles navigating between feeding grounds and nesting beaches lose their coordinate system. Honeybees, which use the field partly to calibrate their orientation within the hive, experience disruption to their communication dances. This is not immediately visible to humans. These animals do not stop and send a signal. They do not make a sound that we can hear. But in those first hours in the world's oceans and skies and rivers, there is a quiet, invisible crisis unfolding in the biological navigation systems of hundreds of species simultaneously. By the end of hour one, here is what the world looks like. On the surface, almost nothing appears wrong. People are going about their days. The sun is shining. The air is breathable. The temperature is normal. Grocery stores are open. Traffic lights are functioning. The internet mostly works, though some services seem slow or intermittently unavailable. In the sky, something unusual is happening. Auroras, the northern and southern lights, are appearing at latitudes far below their normal range. Reports of unusual light displays start appearing on social media from locations that never normally see auroras.
People in southern France, in northern China, in the southern United States are photographing strange glowing curtains of light in the daytime sky. The displays are vivid, beautiful. People are excited, not alarmed. They do not yet know they are watching the beginning of the end of their protective shield. The charged particles of the solar wind streaming directly into the atmosphere without deflection, creating auroral displays not just at the poles, but across the entire globe. In government agencies and research institutions, however, alarm is setting in fast. Space Weather Monitoring Centers, NOAA's Space Weather Prediction Center in Boulder, Colorado, the Royal Observatory in Brussels, the British Geological Survey's Geomagnetic Monitoring Network, are watching readings they have never seen before. Magnetometers around the world are returning values near zero. Not low, near zero. The duty scientists at these institutions are experiencing something between professional bewilderment and raw terror, because the instruments all... This is not a sensor malfunction. This is not a data error. This is real. The magnetic field of planet Earth has effectively disappeared. And they have no protocol for this, because no one wrote one. In emergency management, there is a concept called the cascade failure. It is the moment when one system fails, and that failure puts stress on an adjacent system, which then fails, and that failure puts stress on another system, and so on. Like dominoes, but each domino is larger than the last. The cascade does not begin with the biggest failure. It begins with a small one, an unexpected one that nobody was watching closely enough. By hour 2 after the magnetic field's disappearance, the cascade has begun, and almost nobody on the surface of the planet knows it yet. Let us start where the first visible cracks appear. Not in the sky, not in government offices, in your pocket, your smartphone. Modern smartphones depend on GPS for far more than turn-by-turn navigation. Location services underpin weather apps, ride-sharing platforms, food delivery, social media check-ins, emergency call routing, and, critically, network timing synchronization. As GPS satellite signals begin degrading due to radiation damage and orbital disruption, the timing pulses that cellular networks use to coordinate their operations start drifting. At first, it is subtle. A call drops unexpectedly. A message sends twice. An app refreshes slower than usual. Individual users assume the problem is local, a bad signal spot, a congested tower, a software glitch. They restart their phones. They move to a window. They do not connect it to anything larger. But network engineers monitoring traffic at major telecommunications carriers are watching something different. They are seeing timing anomalies propagating across their networks in patterns consistent with GPS synchronization errors. They are opening incident tickets. They are escalating to senior engineers, and those senior engineers are making calls to GPS constellation operators asking what is happening to the timing signal. The answers they receive are not reassuring. Meanwhile, a parallel crisis is developing in the global financial system. This is one of the least discussed but most immediately consequential vulnerabilities of modern civilization. High-frequency trading systems, the algorithmic platforms that execute millions of transactions per second across global exchanges, depend on GPS timing to synchronize trade execution across geographically distributed servers. The precision required is not milliseconds. It is microseconds, nanoseconds. When that timing drifts, arbitrage opportunities appear that should not exist. Algorithms begin behaving in unexpected ways. Circuit breakers, automatic trading halts built into exchange systems, begin triggering. By hour 3, Trading anomalies are appearing on exchanges in Tokyo, Frankfurt, and London. They are small. They are being investigated. But the investigations are happening in isolation, each exchange assuming the problem is internal, because no one has yet made the connection between failing GPS timing, degrading satellite infrastructure, and the incomprehensible readings coming from geomagnetic monitoring stations. The financial system is experiencing its first tremors, and it does not yet know why. Now let us look upward, into the atmosphere, at something that scientists have been modeling with increasing precision over the past 2 decades. The ozone chemistry that began in the first hour is accelerating. Research conducted jointly by teams at the University of Oslo and the Finnish Meteorological Institute, published in the journal Atmospheric Chemistry and Physics, examined the ozone impacts of historical solar proton events. Even moderate events, far weaker than what an unshielded Earth would experience, produced measurable ozone depletion at polar latitudes within hours. The Halloween storms of 2003 caused ozone reductions of up to 70% at certain altitudes over the Arctic and Antarctic within just a few days. Now scale that globally. Now remove the magnetic field entirely. Now make it continuous rather than episodic. By hour 4, the nitrogen oxide cascade in the stratosphere is running at levels that have no historical precedent in the human era. The chemistry is relentless. Each incoming particle event adds more catalytic destroyers to the system. The ozone column, measured in Dobson units, the standard scientific measure of atmospheric ozone, is dropping in the equatorial stratosphere at rates that atmospheric models suggest could reach several percent per hour under these conditions. Several percent per hour sounds small until you do the arithmetic. At that rate, meaningful ozone depletion, enough to cause a measurable increase in surface ultraviolet radiation, begins within the first day. But that consequence, the UV increase, is still hours away from being felt on the surface. Right now, the ozone crisis is invisible to everyone except atmospheric scientists watching satellite data with expressions of mounting horror. What is not invisible is what is happening to the sky. The auroras are now unmistakable, and they are not behaving like anything anyone has ever seen before. Normal auroras are creatures of the polar night. They shimmer in greens and purples over Norway and Alaska and Antarctica, driven by charged particles channeled along the magnetic field lines toward the poles. They are beautiful. They are contained. They follow rules. These are not following. Without the magnetic field to channel and concentrate incoming particles toward specific zones, the interaction between the solar wind and the upper atmosphere is happening everywhere simultaneously. The auroras are global. They appear in broad daylight, faint at first against the blue sky, visible mainly as a strange iridescence, a shimmer at the edge of perception that makes people stop and squint upward. But as the particle flux intensifies through the morning hours, they become more vivid, more structured. Curtains and rays of light, normally exclusive to high latitudes, appear over Mexico City, over Cairo, over Bangkok, over Sao Paulo. By hour 5, the daytime aurora is unmistakable to the naked eye across vast portions of the planet. Social media is erupting. The images are stunning. Millions of people are filming vertical phone videos of curtains of green and red light rippling across a blue afternoon sky. Their captions ranging from awe to confusion to the first notes of genuine alarm. The hashtags are trending globally. Scientists are being tagged in post after post, asked to explain. And the scientists who understand what they are looking at are the ones going very quiet.
Because a global daytime aurora is not a beautiful anomaly. It is a symptom. It is the visual signature of the solar wind hitting the atmosphere with no deflection. What looks like a light show from the ground is, in the upper atmosphere, an ongoing particle bombardment. Every photon of that auroral light represents an energy deposition event in the atmosphere, multiplied across the entire sky, continuously. The sky is on fire, in a way that the people filming it cannot yet comprehend. Let us talk about power grids. This is where the physics becomes terrifyingly practical, where the abstract science of magnetic fields and charged particles translates directly into whether the lights stay on in your. When charged particles from the sun interact with Earth's magnetic field, they induce electrical currents in the ground itself. These are called geomagnetically induced currents, or GICs. They flow through any long conducting structure connected to the Earth: pipelines, rail lines, undersea cables, and, most critically, high-voltage power transmission lines. During strong geomagnetic storms, these induced currents can flow into power transformers, saturating their magnetic cores, causing them to overheat, distort the AC waveform they are handling, and in severe cases, fail catastrophically. The canonical example is the Quebec blackout of March 13, 1989. A severe geomagnetic storm, caused by a solar coronal mass ejection, induced currents powerful enough to trip circuit breakers throughout the Hydro-Quebec transmission system. The entire province of Quebec lost power in 90 seconds. 6 million people were without electricity for up to 9 hours. Transformers were damaged across North America. The event is now studied extensively as a case study in grid vulnerability. That storm occurred with Earth's magnetic field fully intact. The field partially moderated the ground currents. The storm was severe but finite. It peaked and passed. Now remove the field entirely. The ground currents are no longer driven by a field perturbation. They are driven by the direct interaction of the solar wind with the ionosphere above, the full, unmoderated force of the solar wind's electrical effects, coupling directly into the ground. The induced currents flowing through power transmission infrastructure are not storm-level currents. They are in a regime that grid engineers have never planned for, because until now, it was considered physically impossible under normal operating conditions. By hour 4, the first transformer failures begin in high-latitude regions: Scandinavia, northern Canada, Siberia. These are the areas most vulnerable to geomagnetically induced currents even under normal space weather conditions, because the geometry of ground current flow concentrates at high latitudes. Grid operators in these regions have invested in GIC monitoring and some mitigation measures precisely because they know their vulnerability. But the currents they are now seeing are beyond their mitigation capacity. Transformers begin to fail. Not all at once, not everywhere, but the failures are real and they are beginning to cascade. Here is the critical detail that makes transformer failures so uniquely devastating. High-voltage power transformers, the massive units that step voltage up and down along the transmission grid, are not off-the-shelf components. They are custom-engineered pieces of equipment. They weigh anywhere from 100 to 400 metric tons each. They take between 12 and 18 months to manufacture. The global spare inventory is extremely limited. In a 2017 report, the American Society of Civil Engineers rated the United States power grid's transformer vulnerability as a critical national security concern, noting that the country had fewer than 200 large power transformers in strategic reserve for a grid that contains tens of thousands. When a transformer fails due to thermal damage from induced currents, it cannot simply be replaced next week. It cannot be replaced next month. It may not be replaceable at all.
if the manufacturing capacity is simultaneously dealing with failures across dozens of countries? Each transformer that fails is potentially a permanent failure. By hour 6 in the highest latitude regions, the first rolling blackouts begin. Not citywide collapses yet, not the dramatic cascades that will come later. Small localized outages in northern Norway, a grid segment going dark in northern Canada, a substation in northern Russia experiencing protective shutdown.
Grid operators are working frantically. They are isolating damaged sections. They are rerouting load. They are doing everything their training has prepared them to do for conventional grid emergencies. But this is not a conventional grid emergency, and the currents are not stopping. There is something else happening in hour 5 and hour 6 that receives almost no attention in popular discussions of this scenario. Something biological. Something happening not in the infrastructure, but inside human bodies. High-energy particles, protons, electrons, heavy ions, interact with living tissue through a process called ionizing radiation. When these particles pass through biological material, they knock electrons off atoms, creating ions and free radicals. Those free radicals damage DNA. They break chemical bonds. They disrupt cellular processes. Sufficient dose causes radiation sickness. Sufficient dose to the wrong cells causes cancer. During the first hours after field collapse, the radiation environment at the Earth's surface is not yet catastrophic at ground level. The atmosphere, all those kilometers of air above your head, still provides significant shielding for the lowest energy particles. A person standing on the ground in a mid-latitude city during hour 3 is not receiving a dose that would cause immediate radiation sickness. But two groups of people are not standing on the ground at mid-latitude cities: airline passengers and astronauts. Commercial aviation routinely exposes passengers and crew to elevated cosmic radiation compared to ground level. At typical cruising altitudes of 10 to 12 kilometers, passengers on polar routes receive roughly twice the radiation dose per hour compared to equatorial routes. Aviation authorities and airline medical advisors track this. Pregnant flight attendants are advised to limit their polar route flying for exactly this. With the magnetic field gone and the particle flux at altitude now dramatically elevated, passengers and crew on aircraft at cruising altitude, particularly on transpolar routes, are receiving radiation doses far beyond any normal flight exposure. Within hours, doses that would normally accumulate over dozens of flights are accumulating in a single journey. By hour 5, the first reports of passenger illness begin. Nausea, headaches, symptoms broadly consistent with the early stages of radiation exposure, though individually easy to attribute to other causes. Flight crews are reporting feeling unwell. Pilots are reporting unusual fatigue. Aviation authorities are simultaneously dealing with GPS navigation degradation and HF communication blackouts. In this environment, the scattered medical reports from individual flights are not yet connecting into a pattern that anyone recognizes as systemic radiation exposure. But in orbit, the situation is already critical, and everyone knows it. The International Space Station sits at approximately 400 kilometers altitude, well above most of the atmospheric shielding. The astronauts aboard have radiation dosimeters. Those dosimeters are running far beyond any reading in the station's operational history. Within the first hour after field collapse, the crew received emergency alerts. They have moved to the most heavily shielded sections of the station, the Russian segment's central node and the storage areas surrounded by water and equipment, which provide additional shielding. Mission controllers at NASA's Johnson Space Center and at Roscosmos in Moscow are running emergency protocols. The radiation dose rate is still climbing. The question being discussed in mission control, quietly, in careful language,
and the way that people discuss things they cannot quite bring themselves to say directly is whether the crew can survive the next 72 hours in orbit. The answer the dosimetry models are returning is deeply uncertain and deeply frightening. By the end of hour 6, the world is at a strange and terrible threshold. On the surface, in most cities, life continues. Shops are open. People are at work. The main topic of conversation, in offices, on social media, in school corridors, is the incredible light display in the sky. The auroras, the shimmer, the curtains of color that have been appearing since morning. But underneath the surface of normal daily life, multiple systems are cracking simultaneously. GPS is degrading. Financial timing systems are drifting. Power grids at high latitudes are failing in localized patches. The ozone layer is being chemically dismantled kilometer by kilometer in the stratosphere. Aircraft crews and passengers are accumulating radiation doses that in normal circumstances would take months to receive. The astronauts aboard the International Space Station are sheltering and waiting for guidance that mission controllers do not yet know how to give. And governments, the ones that have space weather monitoring, the ones that have been receiving the incomprehensible data from their magnetometer networks since hour 1, are convening emergency sessions, behind closed doors, in secure facilities, with advisors who are specialists in space weather, in grid infrastructure, in public health, in emergency management. Those advisors are telling the governments something very difficult to hear. This is not a solar storm. This is not an event with a peak and a recovery. If the magnetic field does not return, and no one currently knows whether it will or when, then every single hour that passes makes the situation worse. The ozone continues to deplete. The transformers continue to fail. The radiation environment continues to intensify as the Van Allen belts fully destabilize. The cascade does not have a natural stopping. There is no playbook for this. There is no international protocol. There is no stockpile of solutions waiting to be deployed. There is only the next hour, and the hour after that. And somewhere in those rooms, someone is asking the question that everyone has been afraid to voice since the magnetometer readings came in. Is this permanent? No one answers, because no one knows, and the clock keeps running. There is a particular kind of silence that falls in a room when experts realize they have no answer. Not the silence of thinking, not the silence of searching for the right words, the silence of genuinely not knowing. The silence of a model that has never been run before, returning outputs that no one wants to read aloud. That silence is sitting in emergency briefing rooms on every inhabited continent by hour 7. And outside those rooms, the world is still waking up, still making coffee, still checking social media, still filming the sky. The gap between what governments know and what the public knows is about to become the most dangerous space on the planet. Let us establish what the science tells us about hours 6 through 24, because this is the period where the invisible damage of the first hours begins converting into visible, undeniable, surface-level consequences. This is where the cascade failure stops being a technical problem in background systems and starts being something that ordinary people experience directly. It begins, as so many modern crises began, with information. By hour 7, the story of the magnetic field collapse can no longer be contained within specialist channels. Space weather enthusiasts, a surprisingly large and technically sophisticated community of amateur scientists who monitor NOAA space weather data, who run their own magnetometers, who track satellite telemetry through public feeds, have already been discussing the readings for hours.
Forums and message boards dedicated to amateur radio and aurora watching have been exploding with data since the earliest hours. These are people who understand what magnetometer readings near zero mean, and they are not staying quiet. The first mainstream media reports appear around hours 7 to 8, depending on the time zone. They are cautious, hedged. The initial framing is of an unusual geomagnetic event. Language borrowed from space weather agencies trying to avoid causing panic while they themselves scramble to understand what they are measuring. But the images of global daytime auroras are everywhere. They are undeniable. They are beautiful and terrifying in equal measure, and the internet is saturated with them. By hour 9, the first scientists begin speaking on the record. Not officially, not through press offices or coordinated statements, but individually, in interviews, in social media posts, in the raw and sometimes panicked language of people who know exactly what the data means and can no longer justify saying nothing. A geophysicist at the GFZ German Research Center in Potsdam, one of the world's premier institutions for studying Earth's magnetic field, operating a global network of geomagnetic observatories, posts a thread explaining what the readings mean. It is technical. It is careful. It is also, between the lines, absolutely terrifying to anyone who reads it closely enough to understand the implications. The thread goes viral within minutes. By hour 10, the word that governments were desperately hoping to avoid is everywhere. Collapse. Public reaction in the first hours after widespread awareness is not, as disaster films would suggest, immediate chaos. It is something more complex, more human, and in some ways more frightening. The initial response is a mixture of fascination, skepticism, and a kind of cognitive paralysis that psychologists studying disaster response call normalization bias. The human brain is extraordinarily good at finding reasons why something unprecedented is actually not unprecedented, why the expert is probably exaggerating, why this has probably happened before and we are all still here, why the institutions will handle it. People go to work. They check the news obsessively between tasks. They text their families. They send each other articles with increasingly alarmed subject lines, but they do not yet change their behavior in any fundamental way. The grocery stores are still open. The lights are still on. The tap still runs water. The normal architecture of daily life is still intact, and as long as it remains intact, the brain insists on treating the crisis as something happening elsewhere, on a screen, in the abstract. This is not stupidity. This is neuroscience. Research by disaster psychologist John Leach, formerly at the University of Portsmouth, has documented that in genuine large-scale emergencies, approximately 80% of people experience a period of behavioral inaction, a stunned, automatic continuation of normal routines, even when intellectually aware that something catastrophic is occurring. Only approximately 10 to 15% respond with immediate, effective adaptive action. The remainder panic or become completely passive. Understanding this psychological reality is critical to understanding what happens in hours 10 through 24. Because the window for effective individual preparation, the window where actions taken now could meaningfully improve survival odds, is open, and most people are not walking through it. The ones who are walking through it are buying food, filling bathtubs with water, withdrawing cash, charging every device they own, finding their camping equipment, calling their moving away from coastal areas if they have reason to understand what a grid failure means for water pumping systems. These people will be better positioned when the next phase begins. Let us now follow the power grid through this critical middle period. Because what happens to electrical infrastructure in hours 6 through 24 determines the shape of everything that follows. The transformer failures that began in high-latitude regions in the early hours are now spreading. Not because the induced ground currents are necessarily stronger at mid-latitudes. They are still more intense in the north, but because the sustained nature of the event is overwhelming protective systems that were designed for brief, intense disturbances, not for continuous, unrelenting current injection. Grid engineers have a tool called a series capacitor, a device that can be inserted into transmission lines to block DC and low-frequency induced currents while allowing the normal AC current to pass. Some grid operators, particularly in Scandinavia and parts of North America, have invested in these devices specifically as GIC mitigation. In normal space weather events, they work well. They are working now, but they are not enough, because the ground current is not behaving like a normal geomagnetic storm current. It is behaving like a sustained global electrical field applied to every conducting structure on the planet simultaneously. And the geometry of the damage is different. In a conventional geomagnetic storm, the worst affected areas are well known: the auroral zones, the regions of steepest magnetic field gradient. Engineers know where to concentrate their defenses. Without a magnetic field, the pattern of induced currents is fundamentally. Mid-latitude regions that normally experience minimal GIC effects are now seeing currents they were never designed to handle, flowing through transformers that have no GIC protection whatsoever. By hour 12, transformer failures are no longer confined to Scandinavia and northern Canada. They are appearing in the United Kingdom, in Germany, in the northeastern United States, in northern China, in Japan. Each failure is still localized. Each one is being managed, isolated, rerouted around. Grid operators are extraordinarily skilled at real-time network management, and the modern grid has redundancies built upon redundancies. But each failure consumes some of that redundancy. Each rerouting puts additional load on adjacent infrastructure. The margins are shrinking. And here is the detail that the grid operators in those rooms know and that keeps them from sleeping, and that they are trying to explain to government officials who do not have engineering backgrounds. You cannot replace a failed extra-high voltage transformer quickly. The manufacturing process involves specialized electrical steel, precision winding of copper conductors around massive magnetic cores, and extensive factory testing. The global supply chain for transformer manufacturing is concentrated in a relatively small number of facilities. Major manufacturers including ABB, Siemens Energy, and GE Vernova operate large transformer plants. But total global production capacity for the largest units is measured in dozens per year, not hundreds. If the current transformer failure rate continues for another 24 hours, the backlog of failed units will exceed global annual replacement capacity. Some of those grid sections will be dark not for hours, not for days, but for months, possibly longer. By hour 18, the first major city-scale blackouts begin. Helsinki goes dark at approximately the 18-hour mark, a consequence of cascading failures in the Finnish national grid combined with import capacity reductions from neighboring Scandinavian networks. The blackout is not total immediately. Industrial load shedding begins first, then rolling residential outages, then a larger cascade as the balancing act becomes impossible to maintain. 6 hours later, following a similar cascade sequence, a large portion of Scotland loses power. Parts of the Canadian Maritime provinces, a section of the Russian Far East. These are not small events. These are major population centers experiencing extended power loss in a context where every backup system, diesel generators, emergency services, hospital backup power, was designed to bridge a gap measured in hours until the main grid recovered.
The main grid is not recovering, and the diesel in the generators is finite. In the United States, federal emergency management is operating at a level of intensity without precedent in peacetime. The National Guard has been activated in multiple states. FEMA is coordinating with state emergency management agencies. The Strategic National Stockpile, normally focused on medical countermeasures for biological and chemical threats, is being examined for anything relevant to a radiation and infrastructure emergency. The President has addressed the nation. The speech is carefully worded. It acknowledges the extraordinary and unprecedented geomagnetic event. It urges calm. It advises the public to stay indoors, avoid unnecessary travel, and follow the guidance of local emergency managers. It does not say what the classified briefings have said. It does not say that the magnetic field appears to be gone and that nobody knows if or when it is coming back. It does not say that the power grid in the northern tier of states is approaching a critical failure.
It does not say that the radiation environment is worsening by the hour. The gap between the public address and the classified briefing is enormous, and it is not sustainable. Because by hour 20, the situation outside is no longer invisible. The ultraviolet light is changing. This is the moment when the ozone crisis, which has been running silently in the stratosphere since hour 1, begins to manifest at the surface in ways that people can physically experience. The ozone column above equatorial and mid-latitude regions has been depleting continuously for nearly 20 hours. The models that atmospheric scientists at NASA's Goddard Space Flight Center and at the Alfred Wegener Institute in Bremerhaven have been running throughout the event are now showing something that forces a difficult conversation. Under the continuous particle bombardment experienced since field collapse, the ozone column depletion rate in the equatorial stratosphere has reached levels analogous to, and in some altitude bands exceeding, the worst Antarctic ozone hole measurements ever recorded. The Antarctic ozone hole, first documented in the 1980s and responsible for elevated UV radiation over southern South America, New Zealand, and parts of Australia each southern spring, represents our best real-world analog for what elevated UV exposure does to ecosystems and human health. But the Antarctic ozone hole was regional and seasonal. What is developing now is global and continuous. By hour 20, ultraviolet radiation at the surface, measured in UV index terms, is climbing noticeably above its solar noon peak values. A UV index of 11 or 12, classified as extreme by the World Health Organization and capable of causing sunburn in fair-skinned individuals within 10 to 15 minutes, is now being recorded at locations that would normally peak at 6 or 7 at this time of year. The UV index is still. People who go outside in the middle hours of the day begin to notice something is wrong, even before they understand why. Sunburn developing faster than expected. Eyes feeling irritated in the bright light. A strange intensity to the light that is hard to articulate. People who work outdoors, construction workers, agricultural workers, delivery drivers, begin to feel the effects most acutely. Emergency rooms begin receiving patients with severe sunburn from surprisingly brief sun exposure. Individual cases are attributed to individual circumstances. Someone who forgot sunscreen, someone with photosensitive medication. But the volume is unusual, and emergency physicians are talking to each other, and the pattern is undeniable. By hour 22, public health agencies in multiple countries issue guidance recommending people avoid direct sun exposure during daylight hours. The guidance is framed carefully, in language about elevated UV conditions related to the ongoing geomagnetic event. It does not use the word catastrophe. It does not say that the ozone layer is being destroyed in real time. But its issuance is itself alarming enough that the social media response is immediate and intense.
Stay indoors during the day because the sunlight is dangerous. For most people, this is the moment when the abstraction becomes real. By hour 24, the end of the first full day, the world has changed in ways that are both enormous and still somehow incomplete. Let us take stock of where we are. Power grids at high latitudes are in active cascade failure, with city-scale blackouts established in multiple countries and spreading. Mid-latitude grids are stressed but largely still operational, held together by the extraordinary efforts of grid operators working without sleep, making real-time decisions at the edge of their system's capacity. GPS is severely degraded.
Aviation has been grounded in many jurisdictions, not by government order in every case, but by the practical impossibility of safe navigation and communication. Maritime shipping is operating at reduced capacity, with vessels falling back on traditional navigation methods and moving cautiously. Financial markets have experienced multiple emergency halts. Several major exchanges have closed temporarily, pending system integrity verification. The cascading timing errors in high-frequency trading systems have been contained, for now, but the economic uncertainty is accelerating capital flight into physical assets, causing unusual market behavior wherever trading is still occurring. The ozone layer is in active, continuing depletion. Surface UV radiation is elevated and climbing. Public health guidance in numerous countries recommends minimizing sun exposure. Agricultural implications for crops, for photosynthetic marine organisms, for the entire sunlight-dependent food web are not yet being publicly discussed, but they are being discussed in scientific emergency sessions. The International Space Station crew has received a combined radiation dose that exceeds the career limits established for NASA astronauts. Mission Control and the crew are in ongoing discussions about emergency procedures. The Soyuz and Dragon capsules docked to the station can be used for emergency return. But re-entry and landing in a severely degraded GPS environment presents its own risks, and the radiation dose during the several hours of return procedure is not trivial. Animal migration and navigation systems are in global disruption. The full ecological consequences will not be apparent for days or weeks, but the disruption has been running for 24 hours and affects every magnetoreceptive species on the planet simultaneously, and the magnetic field shows no signs of returning. The monitoring stations, the network of geomagnetic observatories maintained by institutions including the British Geological Survey, the Institut de Physique du Globe de Paris, and National Geological Surveys on every continent, are all returning the same readings they have returned since hour zero. Near zero, globally, consistently. Somewhere in these hours, in a laboratory that is still operating on generator power, a small team of geophysicists is doing something that will matter enormously in the days ahead. They are looking not at the present, but at the past, at the geological record, at the rocks. Because this has happened before, and the rocks remember. When magma erupts from a volcano and cools into solid rock, the magnetic minerals within it, primarily magnetite, align with whatever magnetic field exists at the moment of cooling. They freeze that alignment permanently into the rock, like a compass needle locked in amber. This is called thermoreminent magnetization, and it is the foundation of the science of paleomagnetism. By reading the magnetic signatures locked into ancient volcanic rocks, lava flows, ocean floor basalts formed at mid-ocean ridges, geophysicists can reconstruct the history of Earth's magnetic field going back hundreds of millions of years. And that history contains something deeply relevant to the current crisis. It contains reversals. Geomagnetic reversals, events where the magnetic north and south poles exchange positions, have occurred hundreds of times in Earth's history.
The record preserved in ocean floor basalts, systematically mapped since the 1960s by researchers including Alan Cox, Richard Dole, and Brent Dalrymple at the USGS, shows a clear pattern of normal and reversed polarity stripes spreading symmetrically away from mid-ocean ridges. This was one of the critical early proofs of seafloor spreading and plate tectonics.
But for our purposes, what matters is not the reversal itself. What matters is what happened during the transition. During a geomagnetic reversal, the field does not simply flip like a switch. It weakens. It becomes disorganized. Multiple magnetic poles may exist simultaneously in different locations. The field can remain at a fraction of its normal intensity for thousands to tens of thousands of years during the transition. And during those periods of weakness, periods that geologists can identify in the rock record, the Earth was not dead. Life continued. The last full reversal, the Brunhes-Matuyama reversal, approximately 780,000 years ago, occurred during the Pleistocene epoch. Early Homo heidelbergensis, a direct ancestor of modern humans, was alive. The megafauna of the Ice Ages, mammoths, cave bears, giant deer, were present. The biosphere survived. Does that mean a field collapse is survivable? Does the geological record offer reassurance? The geophysicists looking at these rocks in their generator-powered laboratory are holding two thoughts simultaneously. Yes, life survived previous field collapses. The biosphere has a resilience that goes beyond any single protective mechanism. And also, none of those previous field collapses happened to a civilization of 8 billion people dependent on electrical infrastructure, GPS satellites, a continuous food supply chain, and an intact ozone layer for agricultural productivity. The geological record can tell us that biology survived. It cannot tell us whether this civilization survives. Those are different questions. And both of them are sitting, unanswered, in every emergency briefing room on the planet as the clock passes the 24-hour mark. The first day is over. The field is still gone. And the worst is still ahead. There is a moment in every large-scale disaster when the emergency stops being a news story and becomes a personal reality. Not for everyone simultaneously. Not evenly. Not fairly. It moves through populations like a wave, hitting the most vulnerable first, the most insulated last, and leaving no one completely untouched. The moment arrives at different times for different people, depending on where they live, what they own, how much they had saved, how close they are to a hospital, how far they are from a working power grid. For hundreds of millions of people, that moment arrives somewhere in the second day, and it arrives wearing the face of an ordinary problem, not a catastrophe, not an apocalypse, something mundane and specific and immediately pressing. The refrigerator stopped working. The ATM is empty. The pharmacy cannot process prescriptions. The tap water pressure has dropped. The phone battery is at 4%, and there is nowhere to charge it. The catastrophe arrives as an inconvenience, and then it stops being an inconvenience. Let us begin with water. Water is so fundamental, so automatic, so invisibly present in modern urban life that most people have never considered the infrastructure that delivers it. You turn the tap, water comes out. The system behind that simple act, the pumping stations, the treatment facilities, the pressure management systems, the chlorination equipment, runs on electricity, continuously, without pause. Water utilities are classified as critical infrastructure in every developed nation, and they have emergency backup power systems precisely because engineers have always understood that water and power are linked.
Most large water treatment and pumping facilities have diesel generators capable of running essential operations for 24 to 72 hours. We are now at the 24-hour mark. Those generators are running. The water still flows, but the diesel is finite. And in a situation where the power grid is not recovering, where the transformer failures are not being repaired but are in fact continuing, the diesel supply becomes a countdown timer. Every pumping station, every treatment facility, every hospital running on backup generator is burning through fuel reserves that were designed to bridge a temporary gap. They are not bridging a temporary gap. They are becoming the primary power source for an indefinite period. Fuel supply chains depend on their own power infrastructure. Petroleum refineries require electricity. Fuel distribution terminals require electricity. The pumps at filling stations require electricity. In grid-affected regions, the cascade moves quickly. The power fails, the fuel distribution system slows, the generators that are keeping hospitals and water systems running begin to face supply difficulties, and the window starts closing. By hour 30, water utilities in blackout-affected regions are beginning to make difficult decisions about load prioritization. Which pumping stations to keep running? Which distribution zones to maintain pressure in? Which systems to let go dark to conserve fuel for hospitals and emergency services? The first water pressure failures appear in residential areas of affected cities around hour 32 to 36. Not complete loss, reduced pressure, enough to make people notice, enough to make people afraid. The response is immediate and predictable. People fill every container they can find, bathtubs, pots, bottles, buckets. The behavior is rational. It is also self-reinforcing. As pressure drops in the distribution system due to simultaneous high demand drawing across thousands of properties, the reduced pressure triggers alarm in more residents, who then also begin drawing water aggressively, which further reduces pressure. By hour 36, in the most severely grid-affected cities, water pressure in upper floors of apartment buildings has dropped to near zero. Residents in high-rise buildings, the standard housing form in most of the world's major cities, have no running water. Think about what that means for a city like Helsinki, or a neighborhood of Edinburgh, or a district of Sapporo. Hundreds of thousands of people in multi-story buildings suddenly without water, without the ability to flush toilets, without the ability to wash hands, without drinking water beyond what they managed to collect in the hours before pressure dropped. Public health implications begin accumulating immediately. Now, let us go to the food system, because by hour 24, a quiet crisis in the global food supply chain is becoming audible. Modern food supply is extraordinarily efficient. It is also extraordinarily fragile. The efficiency and the fragility are the same thing. The system operates on just-in-time delivery principles, meaning that food is not stockpiled in large quantities at any point in the chain. It moves continuously, from farm to processor to distribution center to supermarket to consumer, in a flow that depends on transportation, refrigeration, communication, and financial transaction systems working simultaneously. Remove any one of those, the flow stops. We have now compromised all of them simultaneously. Transportation is disrupted by GPS degradation, fuel supply difficulties, and in some regions by direct infrastructure damage from power failures affecting traffic management systems. Refrigeration depends on power, and cold chain integrity for perishable food operates on tight temperature tolerances that backup generators can maintain for a limited time. Communication systems supporting logistics coordination are degraded. Financial transaction systems are operating with reduced functionality. Supermarkets in most unaffected regions, places where the power is still on and the GPS is degraded but functioning at reduced capacity, look superficially normal at hour 24. The shelves are stocked. The refrigerated cases are running. The checkout systems are processing transactions. But look more carefully, and the signs are already there. Certain fresh deliveries have not arrived. The bread shelves are thinner than usual. The manager is on the phone, trying to reach a distribution center that is not answering. The ATM in the vestibule is out of cash. By hour 36, in affected regions, the signs are no longer subtle. Supermarkets in blackout zones are operating on emergency generator power or not at all. Without refrigeration, perishable stock, meat, dairy, fresh produce, has a limited window before it becomes a waste disposal problem rather than a food resource. Store managers face an impossible choice. Sell the perishables quickly at whatever price clears them before they spoil, or attempt to hold normal operations while the situation resolves. In the absence of clear guidance, different stores make different decisions, creating price chaos and supply confusion. In regions where power is still on, the news from blackout zones is driving panic buying. The psychology is simple and ancient. If others are running out of food, I need to secure my food now before everyone else does the same thing. The panic buying creates the shortages it is trying to prevent. Store shelves that were stocked this morning are empty by early afternoon. Restocking shipments that would normally arrive tonight are delayed or absent. By hour 40, governments in multiple countries implement emergency food distribution protocols. Military logistics assets, trucks, helicopters, distribution personnel, are redirected toward food and water delivery to the most critically affected populations. The scale of the need vastly exceeds the initial response capacity.
Let us talk about medicine, because this is where the human cost of the infrastructure failure becomes most immediate and most irreversible. Hospitals are running on backup power. Most large hospitals have diesel generator capacity sufficient for several days of essential operations: life support, surgical suites, intensive care, emergency rooms. That capacity is being consumed. But hospitals face a problem beyond their own power supply. The medications that keep millions of people alive require refrigeration. Insulin, essential for tens of millions of diabetic patients worldwide, must be stored between 2 and 8 degrees Celsius. The global cold chain for insulin and other temperature-sensitive biologics, vaccines, certain cancer treatments, monoclonal antibodies, has been running on backup power since the blackouts began. At hour 36, the first reports appear of insulin storage failures in community pharmacies that have lost power and have no generator backup. Dialysis patients, people with kidney failure who require machine-assisted blood filtering 3 times per week, need powered dialysis machines and a continuous supply of treated water. Both are now at risk in affected regions. The number of people worldwide requiring regular dialysis is approximately 3.5 million. In blackout zones, dialysis centers are triaging, prioritizing, making decisions that no medical professional ever wants to make. Ventilator-dependent patients in home settings, people with severe respiratory conditions who sleep on mechanical ventilators, are in immediate danger as home power fails. Emergency services are overwhelmed. Every ambulance, every emergency response unit in affected cities is running at beyond maximum capacity. The medical system, like the power grid and the water system, was designed with redundancy for temporary emergency. It is now being asked to sustain indefinite operations under resource constraints for which it was never designed. By hour 42, triage decisions are being made in affected hospitals that will not be publicly reported for weeks. Decisions about who receives the remaining generator power for their life support. Decisions about which surgeries can be postponed and which cannot.
Decisions made by exhausted medical staff who came to work for a normal shift 36 hours ago and have not gone home. Now we need to go back to the sky, because the ozone situation has entered a new phase. The atmospheric science team at the Alfred Wegener Institute, working through the night on generator power in Bremerhaven, has been running continuous atmospheric chemistry models fed by satellite data. The satellites, still operational, primarily the ESA's Sentinel series and the remaining functional NOAA weather satellites. The numbers they are producing are being shared with government scientific advisors in real time. The news is not good. By hour 36, the ozone column above the equatorial and subtropical regions, areas covering the most densely populated latitudes on Earth, has declined by an estimated 20 to 30% compared to pre-event levels. The decline is not uniform. It is deepest in the altitude bands between 20 and 30 kilometers, where the nitrogen oxide chemistry is most efficient, but it is measurable across the entire stratospheric column. A 20 to 30% ozone column reduction translates, by atmospheric photochemistry models published in the Journal of Geophysical Research, to a surface UV index increase of roughly 20 to 40% above normal solar noon values. On a clear summer day at mid-latitude, a UV index that would normally peak at 8 to 9 is now peaking at 11 to 13 in the same location. 11 to 13 is classified as time to sunburn for unprotected fair skin, less than 10 minutes. For darker skin tones, the absolute UV damage threshold is higher, but DNA damage in skin cells, a precursor to melanoma, accumulates regardless of burn sensation. By hour 40, in regions where skies are clear and the sun is above the horizon, spending more than 15 to 20 minutes in direct sunlight without complete skin covering and high SPF sunscreen is a genuine medical risk. Not a theoretical future risk, an immediate, measurable, dose-quantifiable risk. Public health authorities are now issuing guidance that would have seemed unthinkable 48 hours ago. Avoid all direct sunlight during daylight hours. Cover all exposed skin if outdoor presence is unavoidable. Wear UV-blocking eyewear. Close UV-blocking window coverings in buildings receiving direct sunlight. The guidance is reaching people through emergency alert systems in countries where those systems are still functioning. In blackout zones, it is spreading by word of mouth, by battery-powered radio, by whatever means still work. In agricultural regions, the guidance creates a terrible paradox. Farmers, the people who grow the food that everyone needs more urgently now than ever before, work outdoors. They have always worked outdoors. The spring planting season in the Northern Hemisphere is either ongoing or approaching, and the people who plant and tend the crops are now being told that outdoor work during daylight hours is a radiation hazard. The agricultural implications are beginning to crystallize in ways that reach beyond the immediate crisis. There is something happening in the oceans that receives almost no attention in the first 48 hours. Understandably, it is invisible. It is slow by human perception, and there are immediate crises demanding every available unit of human attention. But it is because it speaks to the longer arc of what a sustained field collapse means. Phytoplankton, the microscopic photosynthetic organisms that form the base of the marine food web and produce approximately 50% of the Earth's oxygen, are exquisitely sensitive to ultraviolet radiation. Research published in the journal Nature by Osmond Holm Hansen and colleagues has documented that elevated UVB radiation at the ocean surface significantly reduces phytoplankton photosynthesis rates and damages the DNA of these organisms. The annual Antarctic ozone hole has provided a natural experiment in this effect for decades. Studies in the waters around Antarctica during ozone hole season consistently show reduced phytoplankton productivity in UV-exposed surface waters, with effects measurable down to several meters of depth depending on water clarity. Now that experiment is running globally. At elevated UV levels, continuously, the phytoplankton at the sunlit surface layer of every ocean on the planet are experiencing elevated UVB exposure. The damage is accumulating. Individually, each organism's response is microscopic. Collectively, across the vast extent of the world's oceans, the effect on primary productivity, the foundational layer of the marine ecosystem, is beginning. It will not be measurable at the surface for weeks. The ocean is vast, and the baseline variability is enormous. But in the depths of the data, in chlorophyll concentration readings from the remaining operational ocean-observing satellites, the signal is there. The base of the food chain is under stress. By the 48-hour mark, the geopolitical situation has become as complex and dangerous as the physical one. Nations with intact power infrastructure are facing a choice that history has confronted humanity with many times before, in many different forms.
When resources become scarce and systems begin to fail, the pressure to prioritize one's own population, to close borders, to redirect supply chains inward, to stop sharing resources with neighbors is enormous and politically almost irresistible. Several nations with significant fuel reserves have quietly suspended export commitments. A major oil-producing nation has halted tanker departures, citing need to secure domestic fuel reserves for infrastructure emergency operations. The fuel markets, already in turmoil from the financial system disruptions, respond with violent price swings. International supply chains for food, medicine, and industrial equipment are fragmenting. The extraordinary interconnection of the global economy, the system that allows a medication manufactured in India to be available in a pharmacy in Germany the following week, is seizing up. Not collapsing entirely, not yet, but the flow is slowing. And slower flow means that the buffers, the warehouse stocks, the reserve inventories, the safety margins, are being drawn down without being replenished. At the United Nations, an emergency session of the Security Council has been convened. It is the first time in the organization's history that the agenda item is not a conflict between nations, but a physical change to the planet itself. The discussions are fractious. Nations with significant blackout exposure are demanding international resource-sharing agreements. Nations with intact infrastructure are reluctant to commit resources they may need domestically. The scientific briefings provided to ambassadors are painting a picture that nobody in that chamber wants to accept as real. The picture is this: if the magnetic field does not recover, there is no stable end state for modern civilization as currently organized. The ozone continues to deplete. The transformer failures continue to accumulate. The satellite constellation continues to degrade. The food system continues to. The cascade does not have a floor that the existing infrastructure can rest on. The question of whether the field will recover and when is therefore not merely scientific. It is existential, and no one can answer it. In a monitoring station in Nîmes, Germany, one of the oldest continuously operating geomagnetic observatories in the world, established in 1914, a scientist is staring at a readout that has barely changed in 48 hours. The field strength is near zero. It has been near zero since the beginning. But something small, something that requires careful interpretation, something that could be instrument noise or could be signal, has appeared in the data in the last 6 hours. A slight irregular variation. Not a recovery,
Nothing close to a recovery, but a variation, a fluctuation, where before there was essentially nothing, there is now a faint, disorganized something. The scientist calls a colleague. The colleague looks at the data. They look at each other across the room in the way that scientists look at each other when something important might be happening, and neither of them wants to say it out loud and be wrong. They send the data to the network, to the other observatories, to their counterparts at the British Geological Survey, at the Institut de Physique du Globe de Paris, at the USGS in Golden, Colorado, at the Geomagnetic Observatory in Kakioka, Japan. Within 2 hours, confirmations begin arriving. The fluctuation is real. It is appearing in multiple independent data sets on multiple continents. It is not instrument noise. The field is doing something. Something disorganized, something that looks, to eyes trained on paleomagnetic records, like the early signature of a field attempting to reassemble. Not in its previous configuration, not quickly, not reliably, but attempting. It is the first possible sign that the collapse is not, that the geodynamo, deep in the liquid outer core, has not died, but has been disrupted, and that it may, over some unknown timescale, reassemble into something functional again. The paleomagnetic record of previous reversals suggests that partial field recovery during a transitional event can occur on timescales of centuries to millennia. That is not reassuring on a human timescale, but it is something. In Nemec, in the fluorescent-lit quiet of a monitoring station running on generator power, the scientist exhales for what feels like the first time in 2 days. Not relief, not hope, not yet, but something. The field is not entirely dead, and the clock is still running. There is a concept in systems theory called a bifurcation point. It is the moment in the evolution of a complex system where the future splits, where 2 fundamentally different trajectories become possible, and the system, driven by conditions that may seem small, may seem arbitrary, may seem almost accidental, tips toward one or the other. Before the bifurcation point, the system's future is broadly predictable. After it, everything depends on which path was taken. By hour 48, human civilization is sitting directly on a bifurcation point. The faint signal from Nemec has been confirmed. The field is showing disorganized, weak, irregular activity. Not recovery, but not absolute zero. The geodynamo has not died. It has been catastrophically disrupted. Whether it rebuilds into something that can protect the planet on a timescale of years, decades, or millennia remains entirely unknown. And civilization cannot wait for millennia. It can barely wait for weeks. The next 24 hours will determine which trajectory is taken, not because the physics will be resolved in that, but because the human systems, the governments, the supply chains, the social orders, the cooperative frameworks that allow 8 billion people to coexist on a planet with finite resources, are approaching their own bifurcation points simultaneously. What happens in hours 48 through 72 is not primarily a story about physics anymore. It is a story about choices. Let us begin with the radiation environment, because by hour 48, it has entered a phase that requires direct, unambiguous language. The Van Allen belts, those vast, donut-shaped regions of trapped high-energy particles that have been destabilizing since hour 0, have now substantially collapsed as coherent structures. The process was not instantaneous. It unfolded over the first 2 days as the magnetic field that maintained them effectively ceased to function. The particles they contained, protons with energies in the millions of electron volts, electrons at relativistic speeds, have been dumping into the upper atmosphere and escaping into space in an irregular, chaotic process that has contributed significantly to the continued ozone destruction. By hour 48, the belt structure is essentially gone. And what replaces it is something that space radiation scientists at the NASA Jet Propulsion Laboratory and at the European Space Research and Technology Center in Noordwijk have been modeling with increasing alarm. A fundamentally different radiation environment in near-Earth space. Without the belts, without the field, the radiation environment at orbital altitudes is now primarily determined by direct solar wind exposure and galactic cosmic ray flux. Both are constant. Neither is being moderated by any planetary magnetic structure. The result is a radiation environment in low Earth orbit approximately 10 to 100 times more intense than pre-event levels, depending on solar activity and specific orbital.
No crewed spacecraft can operate safely in this environment for extended periods. The International Space Station decision has been made. After 40 hours of continuous consultation between NASA, Roscosmos, JAXA, ESA, and CSA, the 5 partner agencies of the ISS program, the order has been given for emergency evacuation. The Soyuz MS capsule and the SpaceX Dragon capsule docked to the station will both be used. The crew of 7 will split, 3 in the Soyuz, 4 in the Dragon. The re-entry and landing procedures have been rehearsed thousands of times in simulation, but never under these conditions. GPS guidance is severely degraded. Landing zone weather monitoring is compromised by the disrupted satellite constellation. The parachute landing systems are mechanical and will function, but precision targeting depends on navigation systems that are no longer reliable. Mission Control has chosen landing sites with the largest possible target area and the most robust ground recovery infrastructure still operational given the grid situation. The Soyuz will target the Kazakh steppe, its traditional landing zone, in a region where the Russian ground recovery teams are still operational. The Dragon will target open ocean off the Florida coast, a contingency water landing zone with the widest margin for navigation error. The crews conduct their final station securing procedures. They seal compartments. They shut down non-essential systems. They take one last look at Earth through the cupola, the beautiful, curved, blue and white Earth that looks from up here almost exactly as it always has. From this altitude, you cannot see the power outages. You cannot see the disrupted migrations. You cannot see the elevated UV burning down onto the surface. The planet looks the same, but the dosimeters clipped to their suits tell a different story. The hatches close. The undocking sequences begin. On the surface, by hour 48, the geography of the crisis has divided the world into 3 broad zones, each facing a different version of the same emergency. The first zone, call it the dark zone, encompasses the high-latitude regions where grid failure is now essentially complete. Northern Scandinavia, most of Canada above the 50th parallel, large portions of Russia, parts of Alaska. In these regions, the power has been off for between 12 and 36 hours. The diesel in the generators is running low or already exhausted. Water systems are failing. The population is in active survival mode. What does active survival mode look like in a modern northern city in the 21st century? It looks like people burning furniture for heat in apartments that were designed around electric baseboard heating. It looks like neighbors gathering in the same apartment, the one with the wood-burning fireplace, the anachronistic luxury that now makes its owner the most important person on the floor. It looks like the spontaneous, remarkable, historically consistent human response
to collective crisis. Community formation, mutual aid, the sharing of resources, of information, of body heat, of whatever food has been gathered. Research on disaster community response by sociologist Lee Clark at Rutgers University and by Enrico Quarantelli, founder of the Disaster Research Center, consistently documents this pattern. The Hollywood image of disaster as chaos and looting is statistically wrong. Most people in most disasters cooperate. They help strangers. They organize. This is happening in the dark zone. In apartment corridors lit by candles and battery-powered lanterns, people are sharing what they have.
Community networks that barely existed before, neighborhood apps, local Facebook groups, church networks are becoming genuine organizational structures, coordinating food sharing, welfare checks on elderly and disabled residents, information relay. It is extraordinary. It is also not enough, because the resources being shared are finite and not being replenished. The cooperation buys time. It does not solve the underlying problem. The second zone, the twilight zone, covers most of mid-latitude regions where the grid is still operational but severely stressed. Europe south of Scandinavia, the contiguous United States, Japan, China's eastern seaboard. In these regions, the lights are still on, but intermittently. Rolling outages are being managed by grid operators who have now been working without meaningful rest for 48 hours. The ozone depletion is causing measurable UV elevation. The water system is working, but under pressure. Food supplies are strained, but not broken. The financial system is operating in a degraded, partially suspended state. Life in the twilight zone is deeply abnormal, but not yet catastrophic. People are indoors. Schools are closed. Most businesses are closed. The streets are quiet in the way that they are quiet during severe snowstorms. A hunkered-down, waiting quiet. People are following government guidance to minimize sun exposure. They are rationing food. They are charging devices whenever power is available. They are listening obsessively to whatever information channels are still functioning. They are also beginning to see, filtering through from the dark zone, images and accounts that make the trajectory unmistakable. And they are afraid. The third zone, the intact zone, covers lower latitudes and regions with robust grid infrastructure and strong GIC mitigation. Parts of equatorial Africa, Southeast Asia, the Arabian Peninsula, parts of South America. These regions are experiencing the UV elevation and the GPS degradation and the satellite communication disruptions, but their power grids are largely intact. Their immediate survival infrastructure is functioning. Their populations are alarmed, but not yet in active emergency. These regions are also receiving an extraordinary influx of distress signals, resource requests, and in some cases, the beginning of physical migration from more severely affected areas. The three-zone geography is not stable. It is a snapshot of hour 48. The twilight zone is sliding toward the dark zone as transformer failures accumulate. The intact zone is not immune. It is simply earlier in the same process. By hour 50, the agricultural situation demands direct attention, because it is in the agricultural numbers that the longest shadow of this event falls. Spring in the northern hemisphere means planting season. The window during which certain crops must go into the ground, determined by soil temperature, frost dates, and growth cycle requirements, is not infinitely flexible. Miss the planting window for winter wheat, for corn, for soybeans, and the harvest that was going to feed hundreds of millions of people simply does not happen. You cannot plant in August what needed to go in the ground in April.
The combination of elevated UV radiation making outdoor daytime agricultural work a health hazard, fuel disruptions reducing the operational capacity of mechanized farm equipment, supply chain failures affecting the delivery of seed and fertilizer, and grid failures disrupting irrigation systems is creating a compounding agricultural crisis. In affected northern regions, the spring planting season of this year is being severely disrupted. Individual farmers are making individual decisions, working in the early morning and late evening when UV exposure is lower, improvising fuel solutions, planting what they can when they can.
The extraordinary adaptability of agricultural communities is on full display. But the aggregate effect across millions of farms, measured in hectares planted versus planned, is a significant reduction in the Northern Hemisphere's expected harvest. The UN Food and Agriculture Organization, in an emergency internal assessment circulated at hour 52, estimates that if current conditions persist for the remainder of the planting season, the Northern Hemisphere's staple grain harvest for this year could be reduced by between 20 and 40%, depending on region and crop type. That assessment is based on models of the planting disruption alone. It does not yet incorporate the longer-term UV effects on crop growth and yield, which atmospheric scientists are only beginning to quantify. 20 to 40% reduction in a year's grain harvest for a world that already operates with relatively thin food security margins is not a famine in isolation, but it is the beginning of the trajectory toward one, if the conditions that caused it persist. Food security analysts at the World Food Program are running the numbers. The numbers are not numbers that anyone wants to present to a minister or a president, but they are being presented anyway, because the alternative, not presenting them, is worse. Hour 54 brings something unexpected. Not catastrophic, not a new failure. Something that, in the context of 48 hours of relentless bad news, feels almost surreal in its ordinariness. The NEMEX signal has strengthened. Not dramatically, not enough to call it a recovery. The field strength readings coming from the global network of geomagnetic observatories are still a small fraction of pre-event values, but they are measurably higher than they were 12 hours ago.
And the pattern, the disorganized, multipolar, chaotic pattern of the re-emerging field, is showing the earliest signs of spatial coherence. Instead of a completely random noise signal, the data is beginning to show hints of structure, hints of large-scale organization. In paleomagnetism, this signature has a name. It is called an excursion recovery pattern, the signature seen in certain volcanic rock sequences where the field, having collapsed or deviated dramatically during a geomagnetic excursion, begins to reassemble. The Le Champ excursion, approximately 42,000 years ago, left exactly this kind of signature in sedimentary records from across the globe. A collapse, a period of near-zero intensity lasting perhaps a few hundred to a few thousand years, and then a gradual, disorganized recovery. The Le Champ excursion is the closest historical analog to what appears to be happening. During the Le Champ, detailed reconstruction of the field behavior, published by researchers including Jean-Pierre Vallée at the Institut de Physique du Globe de Paris, using sediment cores from lake beds that preserve continuous magnetic records, shows that the field did not simply drop to zero and stay there. It fluctuated. It reorganized. It went through periods of partial recovery before strengthening into something functional again. If the current event is following a Le Champ-like trajectory, compressed for reasons related to the specific dynamics of the geodynamo disruption, then the recovery might occur on a timescale of years to decades rather than the centuries that characterized some historical excursions. The geodynamo has enormous inertia. It cannot restart instantly, but the liquid iron of the outer core is still moving. it is still convecting. The heat from the inner core that drives the dynamo has not changed. The rotation of the Earth that shapes the flow patterns has not changed. The engine is still there. It may be
But here is the critical scientific honesty that the researchers communicating this news insist on maintaining. They do not know. The signal is real. The trend is real. Whether it continues, whether it reverses, whether the recovery takes 10 years or 10,000 years, these questions cannot be answered with the data currently available. The paleomagnetic record tells us what happened in the past, after the fact, preserved in stone. It does not give us a real-time prediction tool with meaningful short-term resolution. When governments ask the scientists, and they are asking, urgently, desperately, in every secure briefing room on the planet, whether the field is coming back, the honest answer is, probably yes. Eventually. The geodynamo has never permanently failed in 4.5 billion years of Earth history. But the word eventually is doing enormous work in that sentence, and no one can replace it with a number. By hour 60, the social fabric is being tested in ways that reveal both the worst and the best of human nature. As it always has, as it always does. The looting that disaster films predict, the immediate breakdown of social order, the war of all against all, is not happening at the scale that the most pessimistic models suggested. The sociological research on disaster behavior that Quarantelli and Clark documented holds true here as well. The majority of people are cooperating. Communities are organizing. Improvised aid networks are forming in the gaps left by overwhelmed official emergency structures. But the pressures are intensifying. And in specific contexts of extreme resource scarcity, of information vacuum, of fear amplified by darkness and uncertainty, the cooperative framework is fraying. In some cities in the dark zone, there have been incidents, confrontations at food distribution points, conflicts over generator fuel. In a small number of cases, violence.
These incidents are being reported, and they are real. But they represent a small fraction of the total human activity in these areas. The overwhelming majority of what is happening in the dark zone is not conflict. It is adaptation, improvisation, mutual aid. What is more systemically threatening than individual incidents of conflict is the political pressure building on governments to make decisions that prioritize their own populations over international obligations. Nationalism, the oldest default setting of political systems under stress, is asserting itself at exactly the moment when the crisis demands its opposite. The resources that could most effectively address the global emergency, fuel reserves, transformer manufacturing capacity, medical supplies, food stockpiles, are distributed unevenly around the world. Addressing the crisis at its most acute points requires moving those resources across borders, sharing them internationally, subordinating national interest to collective survival. This is precisely what political systems find most difficult to do under pressure. The history of international cooperation in crises, from the 1918 influenza pandemic to the 2020 COVID pandemic, shows that genuine sustained resource sharing at the required scale almost never happens as smoothly or as generously as the crisis requires. At the United Nations, the emergency session has been running continuously for 36 hours. Agreements have been reached on some things: a framework for fuel sharing between nations with surplus and nations in acute deficit, a commitment to prioritize the continued operation of food production and distribution infrastructure as a global public good, a scientific coordination mechanism to share geomagnetic data in real time across all monitoring networks. These are real achievements. They matter. But they are smaller than what is needed, slower than what is needed, and contingent on political will that is being eroded hour by hour by domestic pressures in every member state. Hour 66. The ISS crew has landed safely. The Soyuz touched down in Kazakhstan at approximately the 62-hour mark, within acceptable range of the target zone despite GPS degradation. The Dragon splashed down in the Atlantic, further north than the planned zone, driven off course by navigation uncertainty, but within range of recovery vessels that had been pre-positioned. All 7 crew members are alive. All 7 are receiving medical evaluation for radiation exposure. Their cumulative radiation dose over approximately 60 hours aboard the station after field collapse is being assessed. The doses are serious. They are above career limits. They will require long-term medical monitoring for elevated cancer risk. But they are not immediately lethal. The shielding of the station's most protected areas, combined with the relatively short duration, has kept the doses below the threshold for acute radiation syndrome. The crew is alive. It is the first unambiguously good news in 66 hours. It is also a symbol, whether intentionally or not, of something important, of adaptation, of using the tools available, accepting the risks that cannot be eliminated, and making the decision to act rather than to wait for perfect conditions that will not come. In many ways, the ISS evacuation is a microcosm of the larger decision that humanity is facing at hour 66. The conditions are not going to be perfect. The field may not recover on any timescale relevant to the people alive today. The ozone will continue to deplete for as long as the particle bombardment continues. The grid failures will continue to accumulate. The food system disruption will compound. And the choice. The bifurcation point that systems theory describes is not between a good option and a bad option. It is between adaptation and paralysis, between accepting the new reality and acting within it, or waiting for the old reality to return and losing the window to act while waiting. By hour 70, something is happening at the surface level that no model predicted with sufficient emphasis. Something that speaks not to the failure of civilization, but to its deepest, most durable strengths. Across the dark zone, across the blackout regions, the cold apartments, the communities organized around shared candles and shared food, people have begun doing something that their ancestors did for all of human history before electric light made it unnecessary. They are talking to each other, at length, in the dark, in the way that people talked before screens, before the endless fragmentation of attention that connectivity enabled, in the enforced stillness of a world without power, without internet, without the noise that modern life generates continuously. People are sitting together and talking. This sounds trivial against the scale of the crisis. It is not trivial. The social bonds being formed and reinforced in these hours, the trust networks, the mutual knowledge of who has what skill, what resource, what need, are the foundation of the adaptive capacity that the coming weeks and months will demand. A community of strangers who have never spoken to each other cannot effectively share resources, coordinate labor, or make collective decisions under pressure. A community of people who spent 3 days in the dark talking, making decisions together, learning each other's names and circumstances, that community has a fundamentally different capacity for collective action. Disaster researchers have documented this phenomenon repeatedly. The communities that recover most effectively from major disasters are not the wealthiest ones or the ones with the best infrastructure. They are the ones with the strongest pre-existing or crisis-forged social networks. Robert Putnam's foundational research on social capital, published in his 2000-year book, Bowling Alone, and in subsequent work, establishes this relationship with extensive empirical evidence. The crisis is destroying infrastructure. It is not destroying people's capacity to connect. And that capacity, ancient, robust, wired into human neurology by hundreds of thousands of years of cooperative survival, may be the most important resource of all in what is coming. Hour 72. The first 72 hours are ending. Let us take a final accounting, a precise, clear-eyed inventory of where the world stands as the third day closes. The magnetic field is near zero, but showing faint, disorganized, early signs of potential reorganization. No timeline for recovery can be given. No guarantee of recovery can be given. But the geodynamo is not dead. High-latitude power grids are in extended failure. Multiple countries are in darkness, with grid restoration dependent on transformer replacement that cannot happen quickly under any realistic scenario. Mid-latitude grids are stressed but largely operational, maintained by extraordinary human effort against accumulating failures. Low-latitude grids are mostly intact but under increasing stress. The ozone layer has sustained significant depletion. Estimates range from 15 to 35% column reduction across equatorial and mid-latitude regions. Surface UV radiation is elevated to levels classified as extreme across large portions of the inhabited world. The depletion will continue for as long as particle bombardment continues. Recovery of the ozone layer, once particle bombardment stops, would take months to years. The chemistry of ozone regeneration is well understood, and the atmosphere can rebuild the layer, but not instantly. GPS is severely degraded globally. Aviation remains largely grounded. Maritime shipping is operating at reduced capacity using traditional navigation. Financial systems are partially operational with extensive manual intervention and emergency protocols. Food supply chains are significantly disrupted. The Northern Hemisphere's spring planting season has been partially compromised. Global food security margins have narrowed. The full agricultural impact will not be quantifiable for months. Medical systems in affected regions are operating under extreme stress. Insulin and other cold chain medications are at risk in areas without reliable power. Dialysis and other life support-dependent patients in dark zone areas are in critical situations requiring immediate international humanitarian response. The ISS crew has been successfully evacuated. All 7 astronauts are alive. Animal navigation systems remain globally disrupted. Ecological consequences are accumulating but not yet fully apparent. And 8 billion human beings are alive. Frightened, stressed, in many cases cold, hungry, and in the dark. But alive, and overwhelmingly, with exceptions that are real but statistically small, cooperating rather than fighting, adapting rather than collapsing, doing what the species has always done in the face of conditions it did not choose and cannot immediately change. Surviving. The first 72 hours are over. What comes next, the weeks, the months, the years, will be the subject of scientific study, historical analysis, and human testimony for as long as civilization exists to record it. But the first 3 days have passed, and the world has not ended. It has changed, irrevocably, profoundly, in ways that will take generations to fully understand. But it has not ended. The clock has stopped counting down, and a different clock, the clock of reconstruction, of adaptation, of the long, difficult, entirely human work of rebuilding in a changed world, has begun. 3 days. We have walked through 72 hours of a scenario that most people never think about. A scenario that feels like science fiction until you look at the science, until you read the monitoring data, until you sit with the actual numbers coming out of actual instruments operated by actual researchers at actual institutions who think about this, not as a thought experiment, but as a professional responsibility. And now, as we step back from the hour-by-hour reckoning, we need to ask the question that every good investigation must eventually ask. What does this mean for the world we actually live in? Right now, today. Because the magnetic field collapse we have been exploring is not purely hypothetical. It sits on a foundation of real data, real measurements, real trends that are being tracked by real scientists with real concern. The scenario was extreme, a sudden, complete collapse rather than the gradual weakening that is actually observed. But the vulnerability it exposes is not fictional. The vulnerability is entirely, uncomfortably real. Let us begin with what the science actually tells us about where we are right now. Earth's magnetic field is weakening. This is not a fringe claim. It is not contested among geophysicists. It is measured, documented, and published in peer-reviewed literature going back more than a century. The first systematic measurements of Earth's magnetic field intensity were made by the German mathematician Carl Friedrich Gauss in 1835, establishing a baseline that modern measurements can be compared against. Since that baseline, the global average field strength has declined by approximately 9%. 9% in less than 200 years. On a geological timescale, that is extraordinarily fast. The rate of weakening has not been constant. Research published in the Proceedings of the National Academy of Sciences by Nicolas Touvigny and colleagues, using sediment core records from the Mediterranean, has shown that the current rate of field weakening is among the fastest seen in the paleomagnetic record over the past 50,000 years. The South Atlantic anomaly, that vast region of weakened field strength stretching across the South Atlantic and into southern Africa, is the most visible expression of this trend. Its area has been growing. Its minimum field strength has been dropping. Satellites passing through it experience elevated radiation. The European Space Agency's SWARM mission, which has been providing the most detailed picture of the field structure since 2013, has documented the anomaly splitting into 2 distinct lobes, a development that some researchers interpret as consistent with the early stages of a more significant field reorganization. In 2020, a study led by researchers at the University of Leeds, published in the journal Geophysical Research Letters, used swarm data to show that the South Atlantic anomaly has been moving steadily westward and that its structure is becoming increasingly complex. The lead researcher, Dr. Kieran Beggan of the British Geological Survey, was careful in his public statements. Scientists always are, and rightly so. The anomaly does not necessarily indicate an imminent reversal. Field behavior is inherently variable and difficult to predict on short time scales. But the trend is real, and the trend is in one direction. What does the paleomagnetic record tell us about what this trend might mean? This is where the story becomes both reassuring and sobering simultaneously. Geomagnetic reversals, full exchanges of magnetic north and south, have occurred approximately 183 times in the last 83 million years, based on ocean floor spreading records compiled by researchers at institutions including the Scripps Institution of Oceanography in La Jolla, California. The average time between reversals varies enormously, from tens of thousands of years to tens of millions, But the current normal polarity period, which began with the Brunhes-Matuyama reversal 780,000 years ago, is already unusually long compared to the average. We are, statistically speaking, overdue. That statement requires immediate qualification. Geomagnetic reversals do not operate on a regular schedule. There is no clock running, no accumulating pressure that must eventually release. The last reversal could have been 500,000 years ago or 5 million years ago, and the current one could still be tomorrow or in another million years. The overdue framing, while statistically defensible, can be misleading about the actual predictability of the process. What the record does tell us, with high confidence, is how these events unfold when they do occur. The transition is not instantaneous. Based on paleomagnetic records from rapidly deposited lake sediments, which provide finer time resolution than ocean floor basalts, researchers including Robert Muscheller at Lund University in Sweden have estimated that the La Champ excursion, approximately 42,000 years ago, involved a period of severely reduced field strength lasting roughly 1,000 years, with the most extreme low field conditions persisting for several centuries. 1,000 years of weakened field, not 72 hours. And life survived. Completely. The La Champ excursion left no detectable mass extinction event in the fossil record. Homo sapiens, who were present and widespread across the Old World during this period, continued without biological interruption. The Cooper et al. Study published in Science in 2021 examined the La Champ excursion in extraordinary detail, correlating it with climate records, cave painting records in Europe and Australia, and genetic data from ancient human and animal populations. The authors found that the weakened field during the La Champ coincided with significant environmental changes, shifts in atmospheric chemistry, changes in climate patterns, elevated cosmic ray flux, leaving its signature in the carbon-14 record preserved in tree rings and ice cores, but not with human extinction or even significant population reduction. Our species survived a field excursion once before, but, and this is the critical but, our species in 40,000 BCE was not operating 8 billion people on an interconnected electrical grid with a satellite-dependent food supply chain and a population density that requires industrial agriculture to feed. The biological question and the civilizational question have different answers. Biology survived the La Champ. Medieval civilization, or Pleistocene hunter-gatherer bands, would survive a modern field weakening event far more easily than the civilization we have built. Not because medieval people were tougher, but because their systems were not brittle in the same ways. A village farming community loses almost nothing if GPS fails. It loses almost nothing if the power grid goes down. It loses almost nothing if satellites stop functioning. We have traded robustness for efficiency, and the magnetic field scenario reveals that trade with brutal. Here is what scientists who specialize in this field, researchers at the GFZ Potsdam, at the British Geological Survey, at ETH Zurich, at the Institut de Physique du Globe de Paris, actually say when asked about risk. They do not say this scenario is imminent. They do not predict a collapse on any specific timescale. The honest scientific position is that the behavior of the geodynamo is not predictable with the precision that would be needed to give meaningful short-term warnings. The field could continue its current weakening trend for another 1,000 years before anything dramatic happens. Or the trend could accelerate. The science currently cannot distinguish between these possibilities with confidence. What they do say, what the scientific literature consistently reflects, is that infrastructure vulnerability to space weather events is real, present, and insufficiently addressed. This is not about a complete field collapse. This is about the events we already experience with the field in place. The Carrington event of September 1st and 2nd, 1859, a solar storm of extraordinary intensity named after the British astronomer Richard Carrington, who observed the solar flare, produced geomagnetically induced currents that set telegraph equipment on fire across North America and Europe. Telegraph operators reported receiving electric shocks. Some telegraph systems continued operating for hours after being disconnected from their power sources, running entirely on the induced geomagnetic current. The auroras were visible across the Caribbean. If a Carrington-level event struck today, with the current field strength, which is already 9% weaker than in Gauss's time, the consequences for the modern power grid would be catastrophic.
A 2013 report by Lloyd's of London, the global insurance and risk assessment market, estimated that a Carrington equivalent event could cause between 0.6 and $2.6 trillion in economic damage in the United States alone, with recovery taking 4 to 10 years in the most severely affected regions. 4 to 10 years without full grid function. In the country with the world's largest economy, from a storm that occurs with the field fully intact. The risk is not theoretical. It is actuarial. It is being priced by insurance markets, and the mitigation investment remains globally dramatically insufficient relative to the assessed risk. What can actually be done? What do the scientists and engineers who understand this vulnerability actually recommend? The answers are less exotic than the problem might suggest. They are engineering solutions, policy solutions, investment decisions. They are unglamorous. They do not make for dramatic headlines, but they are real and they are achievable. The first and most critical intervention is transformer protection and stockpiling. High-voltage power transformers are the single most vulnerable and most difficult to replace component of the modern grid. The United States passed the SHIELD Act, Secure High-Voltage Infrastructure for Electricity from Lethal Damage, in the House of Representatives in 2016, specifically to address this vulnerability. Its implementation has been incomplete. The strategic reserve of large power transformers remains far below what assessments suggest is necessary. Expanding that reserve and developing geomagnetically hardened designs for the most critical grid nodes is the single highest impact intervention available. Series capacitors and GIC blocking devices can be installed on transmission lines to reduce the flow of geomagnetically induced currents into transformer cores. Finland and Norway, acutely aware of their high-latitude vulnerability, have invested significantly in these protections. The technology exists. The cost is real, but manageable. The barrier is primarily political will and budget prioritization. Satellite radiation hardening standards have improved significantly in recent decades, but the commercial satellite industry, which now operates the majority of the world's satellite infrastructure, operates under less stringent standards than military satellites. As commercial satellites increasingly carry critical civilian functions, this gap matters more than it once did. GPS dependency is perhaps the most underappreciated vulnerability. Modern infrastructure has become extraordinarily reliant on GPS not just for navigation, but for timing. The development and deployment of multiple independent positioning and timing systems, terrestrial timing networks, enhanced ground-based navigation systems, satellite constellations using diverse orbital regimes, reduces the single point of failure risk that GPS currently represents. Ozone layer monitoring and the maintenance of international agreements protecting stratospheric ozone chemistry, primarily the Montreal Protocol of 1987 and its subsequent amendments, which successfully reversed the human-caused ozone hole over Antarctica, represent an existing, functional model of international scientific cooperation producing measurable positive outcomes. That model, and the institutional infrastructure supporting it, has value far beyond its original mandate. And at the most fundamental level, community resilience.
social capital. The networks of mutual knowledge and trust that disaster research consistently identifies as the most important variable in community survival and recovery. These are not built by government programs. They are built by people knowing their neighbors, by communities having shared spaces and shared practices.
By the ordinary, unglamorous, daily work of human connection that modern urban life sometimes makes surprisingly difficult. There is one more thing the paleomagnetic record tells us. One more thing the rocks remember. In the sediment cores from Mono Lake in California, one of the sites used to establish the detailed chronology of the Lechamp excursion, researchers found something that speaks directly to the question of what comes after the low field period, after the chaos of a disorganized, fragmented, multipolar field, after whatever ecological and atmospheric disruption the weakened field permitted. The field came back, not as it was, not immediately, not without the disorganized, complex transitional behavior that characterizes every excursion and reversal in the record, but it came back. The geodynamo reassembled, the liquid iron of the outer core, driven by the same heat and the same planetary rotation that has powered it for 4.5 billion years, found new organizing patterns, new stable configurations, and the field that emerged from the transition protected the planet again. It has done this hundreds of times, through mass extinctions, through ice ages, through the entire evolution of complex life on this planet. The geodynamo has never permanently failed. In 4.5 billion years of Earth history, through every catastrophe the planet has survived, the engine in the liquid core kept running. That is not a guarantee. It is not a promise. Science does not deal in guarantees. But it is a pattern, a deep, consistent 4 billion year pattern. And patterns that have held for 4 billion years carry a certain weight. So where does this leave us? We have walked through 72 hours of the worst-case scenario. We have followed the physics from the collapse of the shield to the cascade failure of the infrastructure, from the chemistry of ozone destruction to the biology of radiation exposure, from the geopolitics of resource scarcity to the extraordinary, stubborn, deeply human capacity for cooperation in darkness. We have looked at the real data, the real weakening trend, the real infrastructure vulnerabilities, the real lessons from the geological record, and we have tried to hold all of it simultaneously, the fear and the hope, the vulnerability and the resilience, the catastrophic possibility and the deep historical pattern of survival. What the science actually tells us is this: the magnetic field is weakening. The rate is faster than the geological average. The South Atlantic anomaly is growing. The infrastructure vulnerabilities to space weather events, events that can happen with the field fully intact, are real, present, and insufficiently addressed. A Carrington-level event today would cause damage that would take years to repair. These are facts. They are not fringe claims. They are published in the most respected peer-reviewed journals on the planet. And also this: the geodynamo has never permanently failed. Life has survived every field excursion in Earth's history. The ozone layer, if particle bombardment stopped, would recover on a timescale of months to years. We know this because we have watched it partially recover from human-caused depletion since the Montreal Protocol. Human communities in disaster after disaster cooperate more than they conflict. The most important infrastructure for survival is not electrical, it is social. These are also facts, also published, also real. The story of Earth's magnetic field
is not a story with a predetermined ending. It is an ongoing story, 4.5 billion years old, and still being written. We are living in one chapter of it, a chapter in which, for the first time, a species on this planet has developed the scientific instruments to read the field, understand its history, model its behavior, and, in principle, take meaningful action to protect against its variability. That is not nothing. That is extraordinary. That is the difference between the Homo heidelbergensis, who lived through the Brunhes-Matuyama reversals 780,000 years ago, with no understanding of what was happening in the field above them, and us. We know. We can measure. We can prepare. We can invest in transformer stockpiles and GIC protection and radiation-hardened satellites and GPS backup systems and community resilience. We can take the scenario we have just explored, the 72 hours, the cascade, the darkness, and use it not as a prediction, but as a design document, a map of the vulnerabilities that need to be addressed before the event rather than after. The question is whether we will. And that question, the one that sits at the intersection of physics and politics, of scientific knowledge and collective will, of what we know and what we choose to do with what we know, is ultimately not a scientific question at all. It is a human one. It has always been a human one. The rocks remember every time the field has collapsed and recovered. They remember the chaos of the transition and the order that followed. They remember the species that survived and adapted and continued generation after generation through conditions that would have seemed impossible to endure. They do not remember the ones that waited for someone else to act. So I want to ask you directly. You have just spent time with this material. You have thought about the ozone layer, and the power grid, and the Van Allen belts, and the cascade failure, and the geomagnetically induced currents, and the phytoplankton and the dialysis patients, and the ISS crew in their shielded compartments watching their dosimeters climb. What do you think? Is this a risk we are taking seriously enough? Is the infrastructure investment being made? Is the community resilience being built? Is the scientific monitoring receiving the funding and the attention it deserves? Or is this another case, like so many in the history of risk management, where we will read the warnings clearly, understand the vulnerability completely, and act only after the event we could have prepared for has already arrived? Tell me what you think in the comments. I read every one. I want to know which part of this story stayed with you, what surprised you, what you think we should be doing differently. Because the rocks remember everything, but they cannot act. Only we can do that. Structure investment being made? Is the community resilience being built? Is the scientific monitoring receiving the funding and the attention it deserves? Or is this another case, like so many in the history of risk management, where we will read the warnings clearly, understand the vulnerability completely, and act only after the event we could have prepared for has already arrived? Tell me what you think in the comments. I read every one. I want to know which part of this story stayed with you, what surprised you, what you think we should be doing differently. Because the rocks remember everything, but they cannot act. Only we can do that.